All right, so we are in week 14 of vibrations with applications. We're nearly done. Today we're going to discuss coupled systems with mixed coordinates. And this section of the book is actually 5.2 and 5.3. And here are some suggested problems. I've already posted some of my solutions, think through 20, and then a part of 521. All right, so here's from the last class, just as a summary, and I will go ahead and use some type of pen or highlighter or whatever. So one thing we should be sure that we do is when we create these equations of motion, we do them based on an FBD and an IBD. But here is our 2 degree of freedom system, and here's the two equations of motion that we would get if we did the FBD IBD, and from that we could get the natural frequencies, aka the eigenvalues, and this is without specifics of K and M, right? So we're just leaving them as variables, and we could. I like to usually move this value to the outside of this square root. And then from those natural frequencies, we could put those back into the equation of motion, essentially, and get the 2 normal modes, aka the eigenvectors. And these will be representative of, like, not a lot of times we'll call them the shape, and that would be true. And if we had multiple degrees of freedom, we only have 2, but they really sort of give the idea of the relative magnitude between the 2 degrees of freedom that correspond with the natural frequency. So with each oscillation, you could see in this first natural frequency of this amount right here, I'm taking the square root of it, you could see that position 1 moves less than position 2, but they are in sync, so they're in phase with each other. And the same thing, or the opposite thing, really is true here, where we have position 1 move significantly more, like more than twice, almost 3 times the amount of position 2, or I should say degree of freedom 2, but in the opposite direction of those 2 things. So let's see. We can find out more specifics of what is actually taking place here if we go ahead and we apply the initial conditions. So that was section 5.2, and I don't think I covered it last week in the week 13 stuff, so we should cover the initial conditions. They sort of gives us a better idea of the actual motion that's taking place. So the equation of motion that we assume is going to be something that looks like this, where we have, so here is our eigenvector values here for positions 1 and 2, right in there. So Ci is the magnitude of that, or the amount that's going to be present for a particular eigenvalue and eigenvector. We also, these might not be working in conjunction with each other. That is, this might not move in the same direction at the same, or it might move in the same direction, but not quite as much. It might be off a bit. So this is the phase angle that we put in there. So we're going to say that's this is a generic value of what it should look like. And the truth is, both modes should be moving. The vibration will contain both modes at the same time. So here is from the book. Here's the values as we place them in there, and we could write these. So what we need to be able to do is find out the C1 and the Psi1 and the C2 and the Psi2. Those are the unknowns. But if we have initial conditions, we're going to be able to generate 4 equations so we can find those 4 unknowns. All right, so here in example 5.2-1, we have these initial conditions. So we should move back to this guy right here. He's being moved 2, and it's positive, so he's moving 2 to the right initially, and this one is being moved 4 to the right, according to this right here. and they're moved there, and then they're let loose. So the initial velocities are 0. So we take that statement that we just had for the set. These are 2 equations, even though they're shown as 1 right there. And then we could take the derivative of them. And now we can replace the initial conditions. So we will take time is equal to 0 and all of these things. And we will set these values here. These are going to be set to 0, and these are going to be set to 2 and 4. So we put those in, and now we just need to, we have 4 equations and 4 unknowns to solve them. But I don't like algebra, so I'm skipping this step. I started to do it, and then I said, well, I don't feel like it. But it can be done because there's 4 equations and 4 unknowns, and the book does a little bit more than I did, but basically they kind of punted as well. But here's the results, right? So it turns out that the phases are going to be both 90 degrees, so they really don't come into play all that much. They just turn them into sine waves, basically. So here it is placed into context there. And so you can see that the sine waves, I guess it doesn't. I guess it turns them into sine waves. Does it not true? No, I'm trying to think about that. Oh no, they're both sine waves, so it turns them into cosine. That's why we have cosine down here. So this is the 2 equations, and here they are plotted versus time. Right, so each one is a position function away from each other, and sometimes they cross each other. Here's positive and negative position as it moves up, back and forth, and back and forth. That's kind of hard to visualize. So I went ahead and I attempted to. Let's see if it'll let me just pick a pen. And can I start this thing? I don't know. Well, let me start it. I don't know. I guess do I need a pointer? Why won't it let me start? Can I go laser pointer? Laser pointer? What if we go backwards? No, it won't let me. All right, so there you go. So you get sort of a sense. In this case, all I did was move this guy, so I didn't actually follow our example, and we're not getting the same results. I moved him over to the left a little bit. Let's see if we can get him to play again. Can we restart? Maybe if I go backwards and then come forwards again. There you go. And now you can kind of see the relative motion. This red line is actually this guy. The blue line is this thing. You can kind of see they're moving towards each other. And then I tried a different set. Now you can see they're kind of moving together and a little bit towards each other, and it's kind of sort of like a little stuttering thing going on. That's all about the initial conditions. This was in SOLIDWORKS simulation, by the way, and you can make your own. It's fairly easy to do. It's not you got to make an assembly to be able to do this, but you could assign mass properties to these pieces. And then you didn't actually have to make this little sled thing. It just seemed like an easy way to try to replicate this problem. All right, so should I make another video here? Sure.